I'm going to be reading from The Autistic Brain by Grandin. I'm starting in the section Lighting Up the Autistic Brain on page 25. I'll probably mispronounce some words. You can laugh if you want, but I think she makes an important point that's worth repeating that isn't being discussed on our national stage today. When I talk about the brain, I often use the analogy of an office building. The employees in different parts of the building have their own areas of specialization that they work together. Some departments work closer together than others. Some departments are more active than others, depending on what the task is at hand. But at the end of the day, they come together to produce a single product, a thought, an action, a response. At the top of the building sits the CEO, the prefrontal cortex. Prefrontal because it resides in the front of the frontal lobe, and cortex because it's part of the cerebral cortex, the several layers of gray matter that make up the outer surface of the brain. The prefrontal cortex coordinates the information from the other parts of the cortex so that they can work together and perform executive functions, multitasking, strategy, inhibiting impulses, considering multiple sources of information, consolidating several options into one solution. Occupying the floors just below the CEO are the other sections of the cerebral cortex. Each of these sections is responsible for the part of the brain it covers. You can think of the relationship between these discrete patches of gray matter and their corresponding parts as similar to the relationship between corporate vice presidents and their respective departments. The frontal cortex VP is responsible for the frontal lobe, the part of the brain that handles reasoning, goals, emotions, judgment, and voluntary muscle movement. The parietal cortex VP is responsible for the parietal lobe, the part of the brain that receives and processes sensory information and manipulates numbers. The occipital cortex VP is responsible for the occipital cortex VP is responsible for the occipital lobe, and part of the brain that processes visual information. The temporal cortex VP is responsible for the temporal lobe, the auditory part of the brain that keeps track of time, rhythm, and language. Below the VPs are the workers in these various divisions, the geeks, as I like to call them. They're the areas of the brain that contribute to specialized functions like math, art, music, and language. In the basement of the building are the manual laborers. They're the ones dealing with life support systems like breathing and nervous system arousal. Of course, all these departments and employees need to communicate with one another. So they have desk computers, television, phones, tablets, smartphones, and so on. When some folks want to talk to others face-to-face, they take the elevator or the stairs. All these means of access, connecting the workers in the various parts of the building in every way imaginable, are the white matter, whereas the gray matter is a thin covering that controls discrete areas of the brain. The white matter, which makes up 3/4 of the brain, is a vast thicket of wiring that makes sure all the areas are communicating. In the autistic brain, however, an elevator might not stop at the 7th floor. The phones in the accounting department might not work. The wireless signal in the lobby might be weak. Before the invention of neuroimaging, researchers had to rely on post-mortem examinations of the brain, figuring out the anatomy of the brain, the answers to what does it look like. Questions were relatively straightforward. Cut it open, look at it, and label the parts, figuring out the functions of those parts. The answer to what does it do the question was a lot trickier. Find someone who behaves oddly in life, and then when he or she dies, look for what's broken in the brain. Broken brain cases continue to be useful for neurology. Tumors, head injuries, strokes. If something's broken in the brain, you can really start to learn what the various parts do. The difference today, though, is that you don't have to wait for the brain's host to die. Neuroimaging allows us to look at the parts of the brain and see what's broken now while the patient is still alive. Once when I was visiting a college campus, I met a student who told me that when he tried to read, the print jiggled. I asked him if he'd had any head injuries, and he said he'd been hit by a hockey puck. I asked where. He pointed to the back of the head. I don't think I was rude enough to actually feel the spot, but I can't say for sure. The place where he was pointing was the primary visual cortex, which is precisely where I had expected him to point because of what neuroimaging has taught us. In broken brain studies, we can take a symptom, an indication that something has gone haywire, and look for the wire or region that's damaged. Through this research, we have pinpointed the circuits in the back of the brain and that regulate perception of shape, color, motion, and texture. We know which are which because they're busted. Weird stuff happens. Knock out your motion circuit and you might see coffee pouring in a series of still images. Knock out your color circuit and you might find yourself living in a black and white world. Autistic brains aren't broken. My own brain isn't broken. My circuits aren't ripped apart. They just didn't grow properly. But because my brain has become fairly well known for its various peculiarities, autism researchers have contacted me over the years to ask permission to put me in the scanner or that scanner. I'm usually happy to oblige. As a result of these studies, I've learned a lot about the inner workings of my own brain. Thanks to a scan at the University of California, San Diego School of Medicine's Autism Center of Excellence, I know that my cerebellum is 20% smaller than the norm. The cerebellum helps control motor coordination, so this abnormality probably explains why my sense of balance is lousy. In 2006, I participated in a study at the Brain Imaging Research Center in Pittsburgh and underwent imaging with a functioning MRI scanner and a version of MRI technology called diffusion tensor imaging, or DTI. While fMRI records regions in the brain that light up, DTI measures the movement of water molecules through the white matter tracts, the inter-office communication among the regions. The fMRI portion of the study measured the activation in my ventral or lower lower visual cortex when I looked at drawings of faces and drawings of objects and buildings. A control subject and I responded similarly to the drawings of objects and buildings, but my brain showed a lot less activation in response to faces than hers did. The DTI scan examined the white fiber tracts between various regions in my brain. The imaging indicated that I am over-connected, meaning that my inner fronto-occipital, I have no idea how to say this, fasciculus, IFOF, excuse me, and inferior longitudinal fasciculus, ILF, I don't know what that means, two white fiber tracts that snake through the brain, that's what that means, have way more connections than usual. When I got the results of that study, I realized at once that they backed up something I'd been saying for a long time, that I must have an internet trunk line, a direct line into the visual cortex to explain my visual memory. I had thought I was being metaphorical, but I realized at that point that the description was a close approximation of what was actually going on inside my head. I went looking for broken brain studies to see what else I could learn about this trunk line, and I found one that involved a 47-year-old woman with visual memory disturbance. A DTI scan of her brain revealed that she had a partial disconnection in her ILF. The researchers concluded that the ILF must be highly involved in visual memory. Boy, I remember thinking, break this circuit and I'm going to be completely messed up. In 2010, I underwent a series of MRI scans at the University of Utah. One finding was particularly gratifying. Remember that when I pointed out the size difference in my ventricles to the researchers after my first MRI back in 1987? They told me that some asymmetry in the brain was to be expected. Well, the University of Utah study showed that my left ventricle is 57% longer than my right. That's huge. In the control subjects, the difference between left and right was only 15%. My left ventricle is so long that it extends into my parietal cortex, and the parietal cortex is known to be associated with working memory. The disturbance to my parietal cortex could explain why I have trouble performing tasks that require me to follow several instructions in short order. This also seems to be associated with math skills, which might explain my problems with algebra. Back in 1987, neuroimaging technology wasn't capable of measuring the anatomical structures within the brain with great precision. But if those researchers back then knew that one ventricle in my brain was 7,093 millimeters long, while the other was 3,868 millimeters long, I guarantee it would have given them pause. How did the two lateral ventricles become so different? One hypothesis is that when damage occurs early in the brain's development, other areas of the brain try to compensate. In my case, the damage would have occurred in the white matter in the left hemisphere, and the left ventricle would have enlarged to fill the damaged area. I'm going to repeat that again. I think this is so important. In my case, the damage would have occurred in the white matter in the left hemisphere, and the left ventricle would have enlarged to fill the damaged area. At the same time, the white matter in the right hemisphere would have tried to compensate for the lost brain function in the left hemisphere, and that expansion in the right hemisphere would have squeezed the right ventricle's growth. The other significant finding from the Utah MRI study included both my intracranial volume, the amount of space inside the skull, and my brain size were 15% larger than the control subjects. This too is likely the result of some sort of developmental abnormality. I don't know if you guys can see this. She's got all kinds of really cool brain scans in here. Okay, showing this. So this too is likely the result of some sort of developmental abnormality. The neurons may have grown at an accelerated pace in order to compensate for the damaged area. The white matter in my left cerebral hemisphere was nearly 15% greater than the controls. Again, this anomaly could be the result of an early developmental abnormality in my left hemisphere and my brain's attempt to compensate by generating new connections. This data reinforces for me the earlier University of Pittsburgh finding that my brain is over-connected. I'm going to say this word wrong and you guys can laugh at me. My amygdala, I don't know. Anyway, whatever that is, are larger than normal. This means the mean of the size of 3 controlled subjects' amygdala, is that what I was saying? Amygdala was 1,498 cubic millimeters. My left amygdala is 1,719 cubic meters, and my right is larger still, 1,829 cubic millimeters, or 22% greater than the norm. And since the amygdala is important for processing fear and other emotions, this large size might explain my lifelong anxiety. I think of all the panic attacks that plagued me through much of the 1970s, and they begin to make sense in a new way. My amygdala are telling me I have everything to fear, including fear itself. Since I started taking antidepressants in the 80s, the anxiety has been under control, probably because the pounding sympathetic nervous system reaction is blocked. But the vigilance to still present percolating under the surface. Wait, let me read that again. But the vigilance is still present, percolating under the surface. My fear system is always on the alert for danger. If the students who live near me are talking in the parking lot under my window at night, I can't sleep. I actually turn on New Age music to block out the sound, even if the students are talking softly. Volume has nothing to do with the fear factor. The association with a possible threat does. Human voices are associated with a possible threat. New Age music isn't associated with a threat. For that matter, neither is the sound of an airplane, so that sound doesn't bother me, even when I'm at a hotel by an airport. A plane could land on the hotel and I wouldn't wake up. The people talking in the next room, forget it. I might as well turn on the light and read because I know I'm not going to sleep until they go to sleep. The chordal thickness in both my left and right, oh boy, I don't know how to say this word, intrahinal cortices was significantly greater than the controls, 12% in the left and 23% in the right. There's that word again. The entorhinal cortex is the golden gate to the brain's memory mainframe. It says it's Fried, a professor of neurosurgery at the David Gifford School of Medicine at UCLA. Every visual and sensory experience that we eventually commit to memory funnels through the doorway to the hippocampus. Our brain cells must send signals through this hub in order to form memories that we can later consciously recall. Maybe this peculiarity in my brain anatomy helps explain my exceptional memory abilities. Naturally, I find these results fascinating because they highlight some of the odd things going on in my brain, that helps make me who I am. But what I find really fascinating is that they match the results of studies of some other people with autism. Preferring objects to faces? These results are typical of individuals with autism. The researchers who conducted the MRI study at Pittsburgh in 2006 later wrote me in a summary of their findings. One thing that seems to be coming up repeatedly in these scanning studies with individuals with autism is a marked reduction in the cortical activation to faces. Enlarged amygdala are often seen in people with autism because the amygdala houses so many emotional functions. An autistic can feel as if he or she is one big exposed nerve. And then there's this, in an email from Jason Cooperrider, a graduate student who led the 2010 imaging study at Utah. Dr. Grandin's head size is large by any standard, consistent with larger than average head-brain size growth in autism. An enlarged brain can be caused by a number of genetic misfires, any of which can result in an early spurt of neuronal development. The growth rate eventually normalizes, but the oh boy, you guys, these medical words are killing me. The growth rate eventually normalizes, but the macrocephaly remains. The latest estimate is that about 20% of autistics have enlarged brains. The vast majority of these seem to be male, for reasons that aren't at all clear. For the first time, thanks to hundreds, if not thousands, of neuroimaging studies of autistic subjects, we're seeing a solid match between autistic behavior and brain functions. That's a huge deal, as one review article summarized the era. The body of research clearly established autism and its signs and symptoms as being of neurologic origin. I'm going to read that again really loud for JFK or RFK Jr. in the back. The body of research clearly established autism and its signs and symptoms of being neurological in origin. The long-held working hypothesis has now become the consensus of evidence and the community. Autism is in your brain. It's not coming from a shot at age 3, guys. It started in the womb, in utero, with the development of the brain. This right here is why everyone is so upset at RFK Jr. and the statements that he made this week. She goes on to say, the problem is, what's in my autistic brain is not necessarily what's in someone else's autistic brain. As a neuroanatomy pioneer, Margaret Bowman once told me, just because your amygdala is larger than normal doesn't mean that every autistic person's amygdala is larger than normal. While some similarities among autistic brains have emerged, we have to be careful not to overgeneralize. In fact, neuroimaging researchers face 3 challenges to find common ground among autistic brains. Homogeneity of brain structures. While the 2010 Utah study revealed several striking anatomical anomalies in my brain, it also showed, as Cooper Ryder emailed me, that for about 95% of the comparisons with the control subjects, the differences were negligible. This overwhelming normalcy in the autistic brain is the rule, not the exception. Why can't I say that word? Anatomically, these kids are normal, Joy Hirsch, an autism researcher then at Columbia University Medical Center in New York, said regarding the subjects in the study of hers. Structurally, the brain is normal on any scale that we can look at, which is not to say that the structure of the brain in her study, or autistic brains in general, don't vary from one brain to the next. They do. But that's true of normal brains too. It's just that the variations among the autistic brains predominantly fall within the range of what's normal. Thomas Insel, director of the National Institute of Mental Health, told USA Today in 2012, shortly after the Centers for Disease Control raised the estimated prevalence of autism from 1 in 110 to 1 in 88. Even when you look at children who has no language, who is self-injuring, who's had multiple seizures, you would be amazed at how normal their brains look. It's the most inconvenient truth about this condition. Nonetheless, some patterns are emerging. In addition to variations in my own brain that seem consistent with those of many other autistics, enlarged amygdala, I can't say that word, lack of cortical engagements when looking at faces. These widespread patterns include avoiding eye contact, different than a preference for objects over faces. This is the active avoidance of faces. A 2011 fMRI study of the Journal of Autism and Developmental Disorders found that the brain is a sample of high-functioning autistics in typical... Wait a minute, let me say that again. A 2011 fMRI study in the Journal of Autism and Developmental Disorders found that the brains in a sample of high-functioning autistics and typically developing individuals seem to respond to eye contact in opposite fashions. And the neurological brain, the right temporopartial junction, TPJ, was active to direct gaze, while in the autistic subject, the TPJ was active to avert gaze. Researchers think that the TPJ is associated with social tasks that include judgments of others' mental states. The study found the opposite pattern in the left dorsolateral prefrontal cortex, and neurotypicals activation to avert gaze, and autistics activation to direct gaze. So it's not that our autistics don't respond to eye contact, it's that their response is the opposite of neurotypicals. Sensitivity to gaze and DLPFC demonstrates that direct gaze does elicit a specific neural response in participants with autism, the study said. The problem, however, is that this response may be similar in processing of avert gaze in typically developing participants. What a neurotypical person feels when someone won't make eye contact might be what a person with autism feels when someone does make eye contact. And vice versa. What a neurotypical feels when someone does make eye contact might be what an autistic feels when someone doesn't make eye contact. For a person with autism who is trying to navigate a social situation, welcoming cues from a neurotypical might be interpreted as adverse cues. Up is down and down is up. Overconnectivity and underconnectivity. A highly influential paper published in Brain in 2004 introduced an underconnectivity theory. The idea that underconnectivity between cortical regions might be a common finding in autism. On a global scale, the major sections of the brain can't coordinate their messages. Since then, numerous other studies have made the same argument, finding a relationship between underconnectivity between cortical areas and deficits in a variety of tasks related to social cognition, language, and executive function. In contrast to this long-distance underconnectivity, other studies have found overconnectivity on a local scale. Presumably, this overgrowth occurs in ways I've already described, an attempt of one part of the brain to compensate for a deficit in another. The results can be positive. As I mentioned, I exhibited overconnectivity in an area corresponding to visual memory. Fortunately, I can manage the visuals. I can sit at a consulting session and run the movie in my mind of how a piece of equipment will work, and then I can turn it off when I'm done. Some people with autism, however, don't have an off switch that works, and for them, overconnectivity leads to a barrage of information, much of it jumbled. Which is not to say that the underconnectivity theory describes all autistic brains. Like many initial attempts to describe a solution to a problem, it probably oversimplifies the situation. As a 2012 study from the University of Amsterdam noted, some patterns of abnormal functional connectivity in ASD are not captured by current theoretical models. Taken together, empirical findings measuring different forms of connectivity demonstrate complex patterns of abnormal connectivity in people with ASD. The theory of the paper concluded is in need of refinement. Heterogeneity of causes. Even when researchers do think they found a match between an autistic person's behavior and an abnormality in the brain, they can't be sure that someone else manifesting the same behavior would have the same anomaly. Part of the title of the 2009 autism study in the Journal of Neurodevelopment Disorders captures the situation succinctly. Same behavior, different brains. In other words, just because you're prone to extreme anxiety doesn't mean your autistic brain has an enlarged amygdala. Conversely, when researchers find an anomaly in the brain, they can't be sure that the anomaly will have the same behavioral effects in a different brain, or any effect for that matter. Just because you have an enlarged amygdala doesn't mean that you're autistic. But what if it did? Not necessarily an enlarged amygdala, but what if some neuroanatomical finding or combination of them could serve as a relatable diagnostic tool? A diagnosis based not on behaviors alone, but on biology as well, would make a big difference in predicting deficits and targeting treatments. Doctors and researchers could apply early intervention, even in infancy, when the brain is still highly susceptible to being rewired. Target areas in the brain more locally, rehabilitating parts of the brain that they think they can help, not wasting time on parts that are unrecoverable. I'm going to say that again because I think it's important. Targeting areas in the brain more locally, rehabilitating parts of the brain that they think can be helped, and not wasting time on parts that are unrecoverable. This flies in the face of, again, what RFK Jr. is saying, is that there's some kind of cure to ASD. If ASD is developing in utero, and it's the result of a brain overcompensating and growing in ways to make up for the parts that it's underdeveloped, there's not going to be a pattern to undo this. Like, there's not going to be a way to change the behaviors that the current ASD kids are going through. Okay, going back to her reading. We're also going to test therapies and monitor existing therapies more narrowly. Tailor a prognosis to an individual patient on a case-by-case basis. For the patient, such a diagnosis would have a tremendous psychological benefit as well, allowing him or her to know what's actually unusual. Personally, I like knowing that my high level of anxiety might be related to having an enlarged amygdala. That knowledge is important to me. It helps me keep the anxiety in perspective. I can remind myself that the problem isn't out there, the students in the parking lot under my bedroom window, but the problem is in here, the way I'm wired. I can medicate for the anxiety somewhat, but I can't make it go away. So as long as I have to live with it, I can at least do so secure in the knowledge that the threat isn't real. The feelings of the threat is real, and that is a huge difference. Given the obstacles to investigating autism from a neurological perspective, you might ask whether finding a biomarker is a realistic goal. Yet in recent years, researchers have made tremendous progress toward reaching that goal and now speak of when, not if. We still don't have a litmus test for autism, but we have a basis for it. As the director of the Functional MRI Research Center, Columbia University Medical Center, New York, Joy Hirsch has tried to build that foundation in the search for a litmus test. In a study her group conducted between 2008 and 2010, 15 autistic subjects ranging in age from 7 to 22 and 12 control children ranging from 4 to 17 underwent fMRI scans of the superior temporal gyrus, the part of the auditory system that processes the sounds of speech into meaningful language. The most obvious disability in autism is the disability of speech, she said, regarding the rationale behind the experiment. Our hypothesis was that at the first stage, we could begin to see differences, and they felt they did. Their measure of activity in that region could identify 14 out of 15 of the autistic subjects' sensitivity rate of 92%. Another way that research groups are searching for biomarkers is by taking a sample of autistic and control subjects, focusing on one aspect of the brain that researchers have reason to believe is associated with autistic behavior, and seeing if they can create an algorithm that can tell one kind of brain from another. So this goes on. I mean, this is a whole book. This is just the first. The point isn't to identify the brain, this brain or that brain, as belonging to an autistic person or a neurotypical. It's to find an aggregate that could help identify areas of potential interest that might be biomarkers. Okay, so she goes on for 10 more pages going into all these studies and giving examples and data about how autism is tracked in the brain through development. It's not some outside environmental factor. It's through the development of the baby in utero. So when RFK is saying phrases like they're a burden and they break up families, or I'm paraphrasing, that's pretty terrible to me. That flies in the face. These kids were created this way. it didn't just suddenly happen to them from outside forces. I tend to believe what Temple Grandin's saying here. So if I'm basing my approach to autism as these children were created like this in the womb for reasons that we don't understand, maybe it is a DNA mutation, which I tend to believe more so than anything else. Why are you saying all these horrible negative things about these children? There are many autistic children, many adults, many of who are nonverbal, who went on to do great things in their industry. This is the reason why people are so mad, because you're taking a broad brush and saying all children that have ASD are broken and need to be fixed. And I think it's some outside factor that I'm going to find in 8 months, and we're going to identify it, and then we're going to reverse these changes in these kids. Well, no, you're not. But you know what you are going to do? This rhetoric is going to give the basis for insurance companies to continue to deny coverage for important therapies that these ASD kids need. Therapies that she talked about here that could rewire the brain in very early childhood, so they don't have to overcome the way their brain's wired so hard and struggle with it for so long. They have ways to cope with it. I mean, are you trying to undo people who have spinal deformities? And I mean, are you calling them a burden and a drain to society? Are you doing this with any other type of deformity or disorder? No. So I don't know why you're going after ASD the way that you are. It's not helpful in any way, and this is why the ASD community is so upset. The things that he's chasing are conspiracy theories. There's not a lot of data to back them up. And sure, he could spend billions of our taxpayer dollars on chasing after these conspiracy theories, but the end result is going to be the same. It was debunked. Why not invest in scanning images of brains and seeing how things line up and don't line up? Why not go after the real science and the real information that could really improve ASD children and ASD adults? This isn't going to go away. You're not going to wave a magic wand. But what you're going to do is you're going to create an army of really upset moms who are going to come after the movement for calling our children all those terrible things that you said. If they were created that way, then there's a reason they were created that way. I mean, you were created a drug addict. Are you a terrible drain on society because you were predispositioned to be a drug addict? I mean, some people might say you were, but you overcame your addiction and presumably are giving something back to society. ASD children are not a drain on society. They have symptoms that are challenging and hard to overcome. I know my children are not where they need to be for their pure developmental age, but I reject the notion that they are a burden and that they're just going to sit in a corner somewhere never being able to participate in life. And I should say that I'm a 3-time Trump voter, and I am in no way supportive of this cabinet pick. I'm very disappointed in the rhetoric that's happening right now, and I just wanted to read this so you guys could hear different variations of what people with common sense are looking into for causes of ASD. And it's not the direction that this guy's going. And so that's why we're mad. And that's why we're saying that the rhetoric that he's using is just, borderline evil at this point. Anyway, the rage is real, the frustration is real, the disappointment is real. That's all. And here's the book. Let's see if I can get this to work. The Autistic Brain. Temple Grandin, awesome person. I love all her writings. I love to listen to her on YouTube. I can't emphasize enough what a great contribution she is to the community. She's, as a parent to ASD children. She's my hero and my inspiration.